Okay. Hyperbola is the same definition as an ellipse with one word change. So if an ellipse is the set of all points in the plane for which the sum of the distance between the xy and two foci is constant, do I need to bring Nick back in here? It's good. A hyperbola is the set of all points xy in the plane. What do you think the word change I'm going to make is? Not the sum, the difference in the plane for which the difference of the distance between xy and two foci is constant. These are a lot more fun to graph than ellipses, in my opinion. They're not completely terrible, but I'm going to put, again, a center down, and I'm thinking I need to shrink the grid up just a little bit to do this. No, I'll just move it like this, and we'll keep it. So I'm going to put an axis down. I'm going to graph a center. There's still a center of an ellipse. I'm going to go, if you want to keep this kind of consistent with me, I'm going to go right 3 and left 3, up 4 and down 4, and then right 5 and left 5. And I'm going to label these points, all these sets. Still have a center, which I can label with a capital C, and I'm not going to label that because it's just going to crowd the figure. I think you get that the center point is a capital C. Vertex are the 2 points along the what was the major axis. There is no major minor with a hyperbola anymore. So we're going to call this the transverse axis. Transverse meaning it cuts across. Don't worry, I'll write this down here in a second. We still have M points that I'm going to put, which actually in this case are further from the center than the V's. M points are along the conjugate axis. It's different. And then foci are now outside and they're further away than your vertices are. So those 3 sets of points, and we're still going to use the letters C, A, and B to mean exactly the same thing. C is the distance from center to focus. B is the distance from center to the M points. And A is the distance from the center to the vertices. So I have C, B, and A, little c, little b, little a. I have all these different values. And another change is that in a hyperbola, C is the biggest one of these. A was the biggest one in an ellipse, but C is the biggest one here. And they still form a Pythagorean relationship. So in a hyperbola, it's C squared is equal to A squared plus B squared. There's so much time spent on, like, what's this formula, what's this equation in? You just need to know it's a Pythagorean relationship, and in a hyperbola, C is the biggest of the 3. So it's C that needs to be by itself. 2 other little points before we kind of start drawing this. 2A is what we call the length of the transverse axis. It's the length of the transverse axis. Oops. And 2B is the length of the conjugate axis. So they're not called major and minor anymore. They're called transverse and conjugate. Transverse meaning cuts across. And I'll show you the image here of why this cuts across. And conjugate meaning not that, perpendicular to. The transverse axis goes from V to V. The conjugate axis goes from M to M. And then finally, that difference of distances is 2A. 2a is the difference of the distances. Just like in an ellipse, 2a was the sum of the distances. In this case, 2a is the difference of distances. So that's pretty similar. And another similarity is in the equation. For what we're going to call a horizontal one, the equation is x minus h squared over a squared. The only change is minus y minus k squared over b squared is equal to 1. So just putting a minus in there is actually going to completely change the image. And here's how it's going to play out. So all this, and now we're going to finally just draw one of these. These are fun. What you're going to do is you're going to take a rectangle, and you're going to put the rectangle around the m's and the v's. You're going to encapsulate this with a rectangle. Oh, it looks like it's going to be episodes of Jessica Jones. Yeah. Lightning and thunder. Thunder only happens whenever it's raining.
It's raining now.
Yeah. Like half of you got that. Okay, we draw this rectangle. Next, draw, more like sketch, the diagonals of this rectangle. So if you sketch the diagonals of this rectangle, I'm going to put one here, here, and here. And I'm actually looking at slope, so I'm trying to sketch this in a little bit more of a consistent way. Point here, and oh, I'll just do one more, way up here and way down here. Because if I do that, then I can use a line graphing tool and just kind of sketch a, there we go. That's a diagonal. A perfectly sloped diagonal. And I'm going to do the same thing up here and put a diagonal here and down here and connect. Whoa. There. Oh, I wanted this diagonal to last longer. It's actually somewhat important that your diagonals come outside of the graph itself. And if you're trying to somewhat save on ink, because you know ink's expensive or whatever, you don't need to draw the diagonals actually inside the rectangle. We are more concerned with the diagonals outside than we are inside. But alas, this is just guidelines. So all of this, everything you drew are guidelines. And I mention this because when I was little, the start of a Mickey Mouse VHS tape that we had showed, you can actually see this on YouTube, which is kind of fun. It showed how they drew Mickey Mouse, and one of the ways that Disney animators, pretty much any animators, make it so that every single person draws the image the same way is they use lots of guidelines in the background. On Blu-rays of some of the animated movies, you can actually see this. You can actually pause the movie and you can see some of the sketchings in the background of where the pencils that they erased to help you guide where to draw this. This is a guideline. We are now going to draw the hyperbola, and this is going to be incredibly not complicated. What you're going to do is take your pencil, put your pencil on the vertex, and you're going to draw out to this as an asymptote. You'll never hit it. So take your pencil, put it on the vertex, and draw out. That's all. Do that 3 more times. Pencil on the vertex, draw out to the other end. Pencil on the vertex, draw out. Pencil on the vertex, draw out. The diagonals of that rectangle act like asymptotes. This is not a not a double parabola, as some people call it. A hyperbola is a much wider and much differently defined shape. It is more like an ellipse that has blown up. And that's what you kind of need to perceive here a little bit. This is an ellipse that has exploded. The foci have now moved outside, causing the object to implode. Okay, that is a horizontal one. We are going to start with our next one and do a vertical one. I want to show how this plays out. And we're going to do this because the equation of a vertical ellipse is just going to be slightly different. In an ellipse, what determined horizontal versus vertical was which number was bigger. And in a hyperbola, what's going to determine whether it opens left and right or opens up and down is which number is positive. So the standard way that we write a vertical is we actually flip the x and y. We make it like this. Y minus k squared over a squared minus x minus h squared over b squared is 1. It really doesn't matter in a hyperbola which one you call A and which one you call B. What matters is that it's still this A goes with Y and the B goes with X, and that's kind of how it plays out. It doesn't necessarily matter which one we call A and B. The way I have it here is that since Y is positive, Y will now be the transverse axis. So A goes with the transverse axis. That's why it's done that way. So let's do one that should make this make a little bit more sense to you. Example. I'm going to do a ton of things in this example to kind of summarize or simplify what we're doing. 4x squared minus 3y squared plus 8x plus 16 is equal to 1 or equal to 0. So just like before, you're going to complete the square. However, you should be able to anticipate that this is going to be a hyperbola, not an ellipse. Right? You can tell.
Minus 3y.
It's the difference of 2, not the sum of 2. You also will not be able to necessarily tell that this is going to be a vertical or horizontal just yet. And I'll show you why that is. This looks like it's going to be a horizontal because the x is positive and y is negative. That's actually going to completely flip around here in a second. Let's take 4x squared plus 8x minus 3y equals negative 16. This is the step that I did. Tim, we did this with you earlier when we just move everything over, make it kind of set up for this. Then we're going to factor the 4 out. Now I get questions about what am I supposed to factor out of the y squared to make that part complete. Actually, the y squared is already complete. With no other terms present, that's y minus 0 squared. So we just keep this as negative 3y squared equals negative 16. Then I'm going to add to both sides, so plus 2x plus 1 minus 3y squared equals negative 16. We added a 1 on the left, which is really not a 1, it's really a 4. So I get 4x plus 1 squared minus 3y equals negative 12. Or 3y squared minus 4 times x plus 1 squared is equal to positive 12. So I just switched everything around. This is why now it's a y squared first, not an x squared first. Divide and we get y squared over 4 minus x plus 1 squared over 3 is equal to 1. So now we're going to start to graph this and dissect all the different pieces. I'm going to keep this to the actual scale that it is, so no rescaling, but we know that a squared is 4, which means that a is 2. We know that b squared is 3, which means that b is root 3. And I know that c squared would have to be 4 minus 3. Kidding, 4 plus 3, because c squared plus equals a squared plus b squared. That's 7, so c is root 7, which you don't know, but it's about 2.6, so that you can graph it. Okay, let's put the center down at 0, or negative 1, 0. It's worth kind of pulling that out so you don't mess that up in your object. Remember, x goes with x and y goes with y. So negative 1, 0. This is a vertical ellipse, or vertical hyperbola, which means that my a's go up and down. I know that because y is first. So I'm going to go up 2 and down 2. Left root 3 and right root 3, and we know root 3 is about 1.7. And then we're going to go up to 2.6 and down 2.6 and put the foci in. It's almost anticlimactic once you graph all of that. Given that I'm not on a grid and not really on anything nice, I just have to do my sketch as best I can. So I'm going to draw the rectangle around. Then I'm going to draw my guidelines. Please be extremely, extremely careful to put your pencil on the vertex, not on the focus. The focus has never been a point that's actually on the graph of any of these. And I'm just going to put that there and draw out to hyperbola are very wide. That is a vertical one. It's worth showing you. Transverse axis, that is this thing. It's the one that cuts down and cuts transverse, cut across. What's this one called? Conjugate axis. Okay, some other terms that come up in an ellipse. You sometimes see this referred to as the sum of the focal radii. That's what 2a is. They call it, if you think about the sum of focal radii, it makes sense. From any point, the sum to the two foci, which would be focal radii, is constant. In a hyperbola, it's not called the sum of focal radii, it's called the difference. The difference of the focal radii. So just for the purposes of visualization, I want you to actually, in your head if you want to, or on your page if you want to, we're going to put a point here on the ellipse, or on the hyperbola, if you want to say ellipse. I'm going to draw that distance out to here, and I'm going to draw the same distance out to the other one. What's happening is that no matter how I do that, the difference of the two line segments, that difference is constant, and that difference is the same as the distance from vertex to vertex. It's difficult to track, and we wouldn't have time right now to draw the complex image needed to derive and prove it. We may tomorrow. But I do, before you guys start squeaking out of here, I want to generalize, because tomorrow is going to be word problems and just a little bit more dissection of this and figuring out where its lateral recta are and all that. The generalization is with this. I can now throw down the word conic. Conic is an adjective describing all the figures that we have done so far. Conic sections can be anything that comes from these equations. ax squared plus bx squared plus cxy plus dx plus ex plus f equals 0. Now, I'm going to do a little subset of this and say when capital C is equal to 0, because that knocks that term out, a term we haven't really seen yet. Okay, and I want you to tell me what shape you get when A or B is equal to 0, but not both. If A is equal to 0 or B is equal to 0, what shape do you get? What's that called if I knock out one of the square terms but I keep the other square term? That's a parabola. What do you get when A and B are both 0? You get a line. Good. When A and B are both 0, you're now down to a linear thing. What do you get when A is equal to B, but they're not 0? A circle. When A is equal to B, you get a circle. It is possible you get a circle, or maybe you get nothing, and that's only going to happen if you have A and B the same, but somehow the math works out so that it's equal to a negative number at the end. You have two squares equaling a negative, but most of the time it would be a circle. What do you get when A and B are the same sign? That's an ellipse. of which a subset could be a circle. And finally, what's the condition necessary for a hyperbola? Yeah, A and B are opposite sign. What do you think the xy term that we knocked out does? It's kind of a neat effect. You can play around with it if you want to. It takes any of these images, any of the ones we've done as up, down, left, right, and it tilts them. So given that, you can actually position any of these figures with any wideness on any part of the graph at any time. Okay, we're going to stop there.